Hi everyone, and welcome to the section 5.3 video on evaluating definite integrals. So just, to remind us from the previous video, we have definite integrals, which remember had this form integral a to b, where a and b were numbers, of some function f of x dx. And what we did was we defined this to be that limit. So this was, remember, the limit as the number of rectangles went to infinity of add up the area of the rectangles. So our connection here was that this, not always exactly, but the general idea was you could think of this like area under the curve. Right? So this was like an area calculation for f of x. And so the general picture you can have in your head is this is a, this is b. We're trying to calculate this with this antiderivative. And again, you have to be careful. What if the function drops below the x-axis? How do we deal with that? We talked about in the last video, but again, I don't think it's a bad thing to just have this pop into your head whenever you see an integral. Just have to remember that these little pictures we give ourselves aren't always perfect, and we have to, learn all of what's going on with this. So with all that said, that was the idea. Now, we talked about calculating this and it kind of being like, I don't want to do the limit, right? That doesn't sound fun, just like for derivatives. That doesn't sound very fun, doing a limit. And so what we do in this section is we're going to learn how to find rules for this. And then when you start Calc 2, you're going to be working on a bunch of rules for this. And so we'll kind of get started with this, laying the foundation with some toolbox functions that you can have and just know antiderivative, what is that, what is that, what is that? Or integral, what is that of x squared, sine, cosine. You'll have that in your toolbox at the end of this class, and then you'll just use those plus new ideas to expand in Calc 2. So how are we going to do this? The way we're going to do this is we're actually going to be using antiderivatives, which again probably is not at all clear why that would play into calculating the area under this curve. So I totally understand why right now it could make no sense why an antiderivative would matter in this picture. But before we get to the why, just to remind us, right, it's been a few sections, the antiderivative, which we usually use big F for, the antiderivative big F of little f is just the function that when I take the derivative, I get down to little f. So remember, we can draw this little diagram. You have big F, little f, and then to go from here to here, you take the derivative. To go backwards, we take the antiderivative. So we are usually given little f, and we figure out a big F that fits the diagram. That's the idea, and that's how you've done antiderivatives up to this point. I give you a function little f, you figure out, what function can I make that its derivative gets me to this little f that I have. There's an example here, little f of x, if that's 3x squared, the antiderivative has to be x cubed, because when I take the derivative to go back down, I drop the 3 minus 1 on top. Boom. Okay? But remember, this is just an antiderivative. There are many, many, many general antiderivatives because I can always add a number to this, right? So just as another example, if you let f of x, just to keep going with this, be 3x squared, then again, we just want to fit the diagram. Big F could be x cubed minus 4, right? Does that fit this diagram? Well, take the derivative. The derivative, big F prime, is 3x squared, and then derivative of a constant 0, so I'm just done, and that's our little f. So yep, fits perfectly. So just as a reminder that in general, when I take the antiderivative, I don't just get one function, I get a ton of functions. And we were labeling that with a plus c, where c is just any constant you want. Could be 0, could be 1/2, could be pi, could be negative 1,000, anything you want. So you've done a bunch of practice on antiderivatives, just reminding you what they are. Now, how does this play in? Well, there's a theorem here, which I'm just going to state, and then we're going to talk about how you should think about this being true, or why it should be true. Here's the theorem. If you have f as a continuous function from a to b, then the integral of f of x from a to b. Now remember, this was just your picture. This integral, I don't need to rewrite the integral, was this picture that's kind of in our head, right? A to b, we've got some function f of x, and I want the area under this curve. Right, that's our quick picture. Like, okay, what was this thing again? So if we have this definite integral here that's somehow representing area in a geometric picture, then we can very quickly solve this. No limit, no rectangles, none of that, by doing the antiderivative of the function in here, plugging in b, then subtracting, plugging in a. That's all you have to do. So this crazy limit with the testing points of the rectangles and the multiply by the delta x and then take the limit, all of that stuff, we can actually forego all of that, just find the antiderivative of little f, which becomes big F, and plug in the 2 points, a and b, that you have. So as a quick example, just to show you the mechanics of this, although we're going to do a bunch in a second. If I wanted to do the integral from 1 to 3 of 3x squared, just to use the work we already did, I could try to set everything up with the Riemann sum and the limit, but I'm going to use the evaluation theorem. That says do the antiderivative of this, which we just said was x cubed, okay, and then evaluate it from 1 to 3. And this is notation you'll see, which tells me, okay, I've done the antiderivative, but now I still need to use these two x values. And then what do we do? Well, the theorem says just plug in the top, okay, 3 cubed, then plug in the bottom, minus 1 cubed, which is 26. There you go, all done. So I've done my definite integral using the evaluation theorem. You find the antiderivative, you plug in. So that's super nice. That's way less work than trying to find a formula for the Riemann sum in general and then use a limit as n goes to infinity to figure out what that's going to approach. Nope, we don't have to do that. We can just find the antiderivative and plug in the endpoints. So you might look at this and be like, what? And that would be totally fair. Because right now it might not be clear why this is happening. But we're going to talk about this in 2 ways. First in general, and then we'll do like a little example, like a toy example with us in a car, something like that. So just in general, let's look at what this says. Remember this connection. This is very, very important. Big F is this function, and I know the derivative is little f. So then what does little f represent? This represents change in big F, right? The derivative represents change, the slope of the tangent line at any point in your function big F. So I think it's actually easier to start right here. So let's start on the right side. What is this supposed to be? F of b minus f of a. Well, if I just have some function, so over here we'll I'll just put it down here. Here's some function. Now we're going to draw big F. So maybe at A, big F is here, and at B, big F is up here. Okay? And it could do a lot of different stuff in between there. So maybe that's my function big F. So then f of b minus f of a, if we just kind of want to draw it on this picture, is going to, if I just over here and over here, this one here is f of b, and this is f of a. So all this is going to do is going to measure the total change. So this here is going to be, so fb minus fa will be the total change in f from a to b. Okay, so just between a and between b, what happened to f, right? In this case, fa was down here, and then by the time it got to b, it was up here. So I would subtract the two numbers and tell you, okay, between a and b, f changed this amount. Right? Now, here's the thing. It didn't just linearly change like that, right? It went up some, and then went down some, and then went up some. That's not what I'm calculating. I don't care how much it goes up and then down and then up and then down in the middle. All I care is at the end, from beginning A to end B, what changed? What was the change? And that's just FB minus FA. So, okay, that's hopefully not too bad. It's just how did big F change between those two values? So that's the right side, the actual change between a and b of my function, the y value of my function. So then how does that connect to this integral, right? This area under a curve. What the heck's going on there? Well, let's think about what this is. What is little f? Little f is the change in big F. So what did we talk about with the integral sign? We said that that's supposed to kind of, the idea is it's supposed to be like a sum. It's adding up. So one way you can think of this integral, instead of area for a second, forget about that for a second. One way you can think about this is kind of like adding up what this little function represents. And what does that function represent? It represents change. So this integral, in a way, from a to b, is just adding up how big F is changing, right? Little f represents the change in big F. It's the derivative. So this integral is just adding up how that change is going from a to b. It starts at a, and then we've got little f. So little f is doing what? It's representing change in big F. So we go a little bit in x, right? We go a little bit in x, and we say, okay, what's f of a plus that little bit? Whatever that number is, that's the slope of the tangent line of big F. It's how much I'm changing. If it's positive, I'm going up, right? If it's negative, I'm going down. If it's a really big number, then big F is changing very fast. If it's a number close to 0, big F is changing not so fast. And so I add that up, and I go a little bit more, and I say, okay, how's big F changing? All right, add that to my kind of total. Okay, go a little bit more. Look at this function again. How is big F changing? Well, what is this function telling me? Okay, add that to the calculation. And so as you go from a to b, very simply, here you could just subtract these two, and that'll tell you the difference. But you could also just keep going along this curve and saying, okay, I'm going up here by a certain amount. Just follow the tangent line a little bit. Okay, add that change. And then I'm going up a little bit more, but not so fast. Add that change, add that change. Ooh, I stopped here. Okay, add that in. Oh, I'm decreasing now. Okay, add that in. That's going to be negative. So, okay, I add that in, add that in. And then, oh, I'm stopped here again. All right, I'm going up. Add that in now to the total. Add that, add that, add that, add that. And that process is exactly this integral. It's the accumulation of changes in big F. So that's what this evaluation theorem says. Plainly, it says I can either know big F and just say the change between A and B will be subtract those two values, or on the other hand, instead of knowing the function for big F, maybe I don't know it, I could know how it changes, little f, and I could add up the change over that time, which sometimes will be positive, sometimes will be negative, but I want those two to be positive and negative when I'm putting them together. But I could just kind of add up the change over the same time period, and that'll tell me the same thing. So this is an incredibly deep idea that is very useful and is going to be in Calc 2, it's going to be in Calc 3, it's going to be all jacked up into multiple variables in Calc 3, which makes it more applicable. Still pretty awesome. So that's the idea. I can either take my big function f and just figure out how it changed from a to b by plugging in and subtracting, or I can do this integral where the idea is I'm just adding up change. I'm adding up change, adding up change, adding up change. That will tell me how big f has changed, because I'm just adding up the change. So that's the idea. Now, that doesn't quite give you the connection to area under the curve. I understand. That's we're talking a little more abstractly with that explanation. So you can always do another explanation where you're trying to actually do something more kind of real life. And so if you heard that and you're comfortable with that, then you can just keep going. But if it's kind of a little foggy here, then you can do something else where you can actually try to use some specific functions or examples here. So let's say this is time. So let's make here velocity, which you could just think of speed, and that's fine. So, okay, we start in our driveway, and then we leave the driveway, and we start increasing speed. Okay, so we start increasing speed, and then we get onto a main road, and we're going 30 miles an hour for a while on the main road. And then we come to a light, and we stop here. Okay, again, back at 0. And then we make a turn, and we get on the highway, and we're going 60 now for a while. Okay, so, and then we'll stop here. All right. So, okay, this graph is showing me over time how fast I'm going. So, change, right? That's the idea, change. So, we're going to call this f of t. So, let's think about this. What, for example, and we'll put some times here. Why don't we put this at, let's see here. We're going 30 miles. We're getting up to 30 miles an hour. That takes us 5 minutes. We'll put this in minutes. And then here would be 10 minutes. And then we'll make this 12 minutes. And then here we'll make this 20 minutes. All these numbers completely made up, but just so we have them. So f of t here is going to be giving us our speed of our car. At any time, we can know how fast we're going. So here's a question. What does this represent? 5 to 10, f of t dt. Okay, well, so we know, let's color code this so we can kind of see this. This is the definite integral from 5 to 10. So, so it's this area. But like what? Forget about area for a second. What is this saying? Well, f of t in that range is 30. So this is equal to, from t equals 5 to 10, I'm going 30. And you could put units on this if you want. We'll do miles per hour, just so we have something here. Miles per hour dt. Okay, so what is this saying? It's saying for 5 minutes I'm going 30 miles per hour. Okay, so what can I do with those two things? I just gave you how fast I'm going and how long I'm doing it for, which hopefully isn't too bad to see, like, oh yeah, I have that formula that I know in my head but maybe never write down. Distance is velocity times time. So, okay, I'm going 30 miles per hour times, and then the total difference here is 10 minus 5, which is 5 minutes, right? So, okay, so I should then be able to, from only knowing the speed and how long I'm going that speed, I can get the total distance that I've traveled, right? So we got to be a little careful here with units, right? This is one of the things that would mess us up possibly. So I've got to convert 5 minutes into hours. So just divide that by 60 and then multiply by 30, and you're going to end up getting that I have gone 2.5 miles. Okay. So what did I just do there? I used my speed and how long I was going that speed. I was able to multiply those together and find the total distance I traveled. But think about this. Where is distance on this picture? It's not this, it's not this, it's nowhere. So distance ends up being area under this curve. And this is exactly what the theorem is telling us right here. It's telling us that you can take this curve that represents change, f of x, in this case f of t, speed. You can add that speed up from A to B, in our case 5 to 10 minutes. And in doing that, this calculation, right, finding area under this speed curve, which we took a simple one because it was just a little rectangle, easy for us to do, we can find the total distance we traveled. That's it. That's the whole idea. And I could do this for any range in here I want to, right? I could find the area here from 0 to 5, from 0 to 10, from 10 to 12. From any of these, we could do this same idea here. And that's it. This area under this curve, right? In this specific case, because I chose a rectangle here, this area is given by the width of this rectangle, which is the time elapsed, times the height of this rectangle, right, which is my f of t. And so that, for a rectangle, that's really easy to do. For things that aren't rectangles, we couldn't just find that area via geometric formula, right? How did we do it? We had to actually do this integral. So that's it. That's the whole idea. This is just telling me, and you could think of it in your head if you are okay with this example, just think of it that way. The integral from time A to time B of my speed is equal to the total distance traveled from A to B. That's the idea. And you can apply to all these different things. Speed and distance is not the only way you can represent something changing, but it's a good one to use. And that's it. That's the idea here. So there's another thing I have to show you before we just start doing these examples and using antiderivatives to solve integrals. And it's something that shouldn't be too bad because we saw this when we first did a derivative. So remember, we did a derivative at a specific point. It was defined to start. Remember the definition of the derivative? The first way we defined that was you had to give me a point first, an x value. Then I was going to define the derivative at that specific value. And then what we realized was, wait, I don't need to start with a value, right? I should be able to make this tangent line, all over the place. I don't need to just pick one x and make the tangent line. I can find a formula where if I just plug into that formula of the derivative, then I can find the slope of the tangent line anywhere on this function I want. And so we're going to do something similar here. This antiderivative, go back to this picture, I can go from 5 minutes to 10 minutes and do this definite integral, right, and spit out a number, how far I've traveled. But you saw how I can pick a bunch of different a's and b's and I could still do this thing. So wouldn't it be nice, right, if there was a way to do this more generally without needing a and b, and then later on, after I figured out what that formula is, that equation, I can bring a and b back in if I need it. So that's the next step, and that is the introduction idea of an indefinite integral. So what we're going to do when we do an indefinite integral is we're going to just forget about this a and b, right? And we're going to use this as a way to represent basically just the antiderivative. So when you see this notation with no a and b, you could still think of it as I'm doing area under a curve, right? But I didn't give you the a and b to go in between. So you're trying to think, instead of getting a specific area and number here, I'm instead going to just see if I can find a formula that lets me later plug in an a and b. And then, so what you do here when you do this is just find the antiderivative. That's all this says. If you see this, it just says to you, find the antiderivative. Okay, so before I said when we were doing antiderivatives in 4.8, this is a little annoying, we don't have a symbol, we don't have a ddx or a prime symbol we can use, like we did for derivatives. an indefinite integral for us is just going to be the symbol we use. If I want to say, let's take the antiderivative of f now, I can just use this indefinite integral sign. And so I don't have to be saying specifically, find the area under the curve from 1 to 3 or -5 to -2 or any of that. I can just say, wait a minute, we could do that later if we want. Let's just get the antiderivative. So that's all of this symbol means. And so from 4.8, all those antiderivatives that we've been practicing can be summarized using integrals. So instead of a table that just says function and antiderivative, we can now summarize that with this table. So, and you'll often hear, instead of antiderivative being used, you'll hear the integral of. So the integral of e to the x dx is e to the x plus c. Why? Well, because the antiderivative of e to the x is e to the x, which we talked about in 4.8. How about sine? The integral of sine x dx is negative cos x plus c. Why? Because the antiderivative of sine x is negative cos x plus c. And then boom, 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 boom. Remember, though, this is not a new thing, really, except for a couple pieces like this one, maybe is a little bit new. But all you have to remember is all of these go backwards using derivatives, right? This is just us, remember, doing that table where we had function and derivative that we had, done back in chapter 3. Well, it's just the reverse of this table. We can always go backwards using derivatives, and so, it's not like you have to memorize a whole new thing here. If you have your derivatives remembered, then this is just nothing. This is going the other direction. So don't forget about that. This is not new necessarily. It's just we're going the other direction between, instead of function to derivative, it's like we're going backwards from derivative down to function. Okay? So summarizing, I know it's a lot. That's just the list of integrals we have at our use now. So let's try some. And we're going to give ourselves a little space here, and maybe we'll zoom in a little bit more too. Okay, so example 1, we've got the integral from -2 to 3, x squared minus 3. So the evaluation theorem, so let's write that down. The evaluation theorem, what does that say? Says this should be equal to big F of 3 minus big F of -2. What's big F? It's the antiderivative of this. Okay, so we just have to find the antiderivative of this. Using our rules, what's the antiderivative of x squared? So we'll break this up into pieces like we did in 4.8. So let's start here. The antiderivative of x squared. Well, what's the rule? Remember, we have the rule. X, add 1, divide. So remember, add 1, divide by that number. That's our rule for antiderivative with the power. Okay. Well, then what about this one? Well, this one's not too bad. Minus, change color, right? Boom. Minus, and then this one here, the 3, a constant always just becomes the constant times x. Now, you might say at this point, well, where's your plus c? You don't need the plus c. And the reason you don't need the plus c is, let's just put it for a second. Like, let's be, how I said, always just saying plus c, plus c, plus c, plus c. Okay, so here it is. Well, let's think about what's going to happen here, right? Plug in 3 into this. This is our, let me label it. Remember, this is our general f of x. So we're going to plug 3 into this minus plug in -2. So watch what happens. And I'm not going to do this every time. I just wanted to show you once what happens. So f of 3, that's going to be 1/3 3 cubed minus 3 times 3 plus c minus, so that was just f of 3 right here. And then I'm going to plug in -2. And I'm going to put a bracket here because we're subtracting all of the stuff we're about to put. 1/3 -2 cubed minus 3 times -2 plus c. Okay, so just focus on the c for a second. I've got a plus c here. this minus is going to travel and hit this and make it a minus c. And this will happen every single time. Plus c minus c will be 0. The constants will cancel. Because remember, the constant is just, you can think of it like a shift. So if I want to know what's happening for f at -2, but you've shifted that function up by 1, well then to figure out how it's going to have changed from -2 to 3, that f of 3 will also have just been shifted up by 1. So I'll have the shift up by 1 in both of those, so they cancel. So you don't care about the c when you're doing a definite integral here. That was my long-winded way to say that. But then this is it. You just start calculating, and you just have to be careful and, not try to mess up the calculation. But in any case, you just go here. So this is going to be 3 cubed, but then there's a 3 here, so that's going to be just 9. Minus 9, so that first piece is actually just 0. Minus. And then we've got to do this one. So this is -8 over 3, but it becomes a positive. So just really watch out here with these pluses and minuses. So that's 8 over 3. This is going to be +6, but the negative comes in and knocks it to -6. And then again, the c cancels. Okay, and we can do this outright. So put a 3 under here, a 3 on top. You're going to get 18. So this is going to be -10/3. Okay, there you go. You just did your first definite integral using the evaluation theorem. A lot easier than trying to find a formula for rectangles and then do a limit. Just find the antiderivative, plug in. Okay, let's try another one. So here's another one. Boop, 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 boop. Get rid of that. So, all right. Evaluation theorem. F of 2 minus f of 1. Now, I'm going to show you notation that's just more common to use than writing it out like this when you're doing this. So, first step, find the antiderivative, which is add 1, divide. Then the notation that's common is to see, so I'll do this in a different color so you can kind of see this. Either you're going to see just a straight line with the bounds written here, the 1 and 2, or sometimes you'll see this as like a little bracket with the 1 and 2 here. It just means the same thing. It's just notation telling you, okay, you've done the antiderivative, but don't forget, you have to still plug these numbers in. So either way you see this written or you write this, this will be -2 to the -1, because I plugged 2 in here, minus, be careful with this, with the minus, minus 1 to the -1. Okay, one way you can just do this every time and not even worry about messing up is plug the 2 in, put a minus sign, put a big old bracket here. Don't even mess around, just put a big old bracket and then plug the 1 in. Then after that, you can start dealing with all of the negatives that are coming in here. So this is going to be equal to -1/2 minus minus is +1 and 1/2. Boom. Whoa. I don't know what just happened there. We're going to leave that in though. So there you go. Take the antiderivative, plug in the bounds, subtract, you're done. Top minus bottom every time. Don't forget about that. Okay, let's try another one. Hey-oh, look at this one. This one's trying to mess us up. Okay. So, first things first, this doesn't look good, right? We don't, just go back to your rules. We don't have any rule that deals with division of all of these different terms. So often you're going to have to start by simplifying algebraically, and that's not too bad. We can totally do that. So we're going to simplify algebraically, and we're going to do that over here first. So I'll do the steps out. How do you simplify this? So this is a fraction that's been combined with a common denominator here, but we actually want to split it up. I know that that's weird and you're used to combining things, not splitting, but you got to be able to adapt here, go both directions. So we split up and then simplify. This ends up just being v to the -1 plus this ends up being 3v squared. So the integral ends up just being 1 to 2 of v to the minus 1 plus 3v squared dv. I'm putting parentheses around here. I think it's clear that you're doing the whole thing in here to dv, but it's nice to just put parentheses around everything that in here that's being integrated. Okay, so we know how to do this. Find the antiderivative. So this is a tricky one, remember. If I add 1 here, I'm going to get 0, and then I can't divide. We got to remember that reverse power rule with the +1 divide does not work if this is -1. So we just have to remember the antiderivative of this is natural log of v. Okay. Then we're going to do plus. Okay, antiderivative of this, add 1 divide. That's going to be v cubed. And then don't forget, I've got to plug in 1 and 2. So let's do it. Plug 2 in. Natural log of 2 plus 2 cubed minus, put the bracket in, natural log of 1 plus 1 cubed. That's equal to natural log of 2 plus 8 minus, natural log of 1 is 0, 1 cubed is 1, which is natural log of 2 plus 7, which is a perfectly fine answer. You can plug this in the calculator if you want to get a decimal approximation, but it's not necessary. This answer is perfectly fine. So antiderivative, plug in the 2, minus, plug in the 1, simplify. Okay, what about this one? So this one, again, maybe looks tricky, but we can algebra ourselves out of this conundrum. So again, we split it up. This is 1 over cosine squared theta plus cos squared over cos squared is 1. This is all now d theta. So okay, that's not too bad, right? Because then this is secant squared, right? 1 over cosine secant. So this is integral 0 pi over 4 secant squared theta plus 1 d theta. Okay. And then we're now in something we can deal with this. Antiderivative plug in. So we just need the antiderivative of secant squared. So then you just got to remember this. And sometimes it's hard to remember some of these trig ones, so just go backwards. The derivative of what function is secant squared? Oh yeah, tan. Tan theta would be the antiderivative here, plus theta, because remember, antiderivative of a constant is just take that number and hit it with the variable. And then we have to plug in our values. 0, pi over 4. That's going to be tan of pi over 4 plus pi over 4 minus, and then plug the 0 in. Put your bracket. Tan of 0. Oops. I started making the circle and it made me want to draw the theta. Tan of 0 plus 0. So we just got to remember the tangent. Pi over 4, sine and cos are equal, so this is 1. Tan of 0, sine is 0, so that's 0, 0. So this just ends up being 1 plus pi over 4. Boom. And there you go. Take the antiderivative. Well, first do a little algebra. Take the antiderivative, plug in your bounds, subtracting in between. And then, you know, got to do some trig simplification here. But just as a reminder, as you're getting ready for Calc 2, do you see how much worse all of this is if you just don't remember some of your trig stuff, your trig antiderivatives, derivatives, your trig values? This problem's going to take you way longer if you're like, oh, what was the derivative of tan is secant or tan of pi over 4? What? Just take some time, if you don't have that down yet, before you get to Calc 2, to save yourself so much trouble during the semester when you're doing all these crazy things in this busy semester. Just get the base values down for your trig functions. Your pi over 4, your pi over 2, right? Your pi over 3. Just go look up a circle and stare at it for a while with all your sine and cosine values. If you need help, you can come talk to me about it. So get those down, make this a lot easier, and boom, there you go. Okay, let's try to do a problem with words in it. And we'll give ourselves a bunch more space here. So, okay, let me zoom over so we can see this a little bit better. Okay, this one says, if oil leaks from a tank at a rate of R of t gallons per minute at time t, what does this integral represent? Okay, so R of t is a rate. Rate makes me think change. This is something you always got to do. If you hear rate, that means change. Okay, so then it gives us the integral from 0 to 120 of R of t dt. Okay, so think about this. Oil is leaking from a tank at this rate. We know that this function is telling us how much oil is leaving the tank at any time t. Right, this instantaneous change. So what is this going to mean if I integrate that function that's representing the oil leaving the tank from 0 to 120? Well, you could think of it this a bunch of different ways, but if you just go back to the evaluation theorem, this is going to be, you could just use big R if you want, big R of 120 minus big R of 0. But what's this big R going to represent? It's going to be the antiderivative. If little r is telling me how much oil is leaving the tank at a specific time, change in oil, amount of oil, gallons, right? Change in gallons per time. So you could think of this as change in gallons per change in time, right? Derivative with respect to t. So then big R is just going to represent gallons. You could just do this from the units, right? Big R, the antiderivative of this, is going to represent how many gallons I have. So then R of 120 minus R of 0 is just going to be how much oil left the tank from t equals 0 to t equals 120. And these are in minutes. That's it. I'm adding up the change. So if I do an integral from 0 to 120 of change of gallons, I should just be able to figure out overall from 0 to 120, how much did we lose? That's it. That's all this integral means. If you're integrating a change, all you're doing is just telling me how much over that time period, A to B, 0 to 120, what was the overall change. So let's see if we can apply that to the next one. A honeybee population starts with 100 bees and increases at a rate of n prime t bees per week. What does 100 plus this integral represent? So I'll rewrite it here so we can fit it. 15 n prime of t dt. So again, n prime of t is a change in bees. This is representing change in bees. So what does integrating this function that represents change in bees from 0 to 15 do? Well, it's just going to represent the number of new bees from t equals 0 weeks to t equals 15 weeks. This integral is just going to represent how many new bees did I get, right? I got a bee population. I know how it increases over time. I do the integral. That just says, okay, add up that change. Tell me what happened. What does the 100 do? The 100 itself just represents the starting population. So the total expression, so that this here was just what does the integral represent? The total expression, right, what's that going to be? Is going to be the number of bees in my population, in 15 weeks. Because the integral tells me how many I have added, because that was representing change, right? And the original 100 is just the original 100 I had. So it's the original 100 I have plus I've added up the change in B's over the 15 weeks to figure out how many new B's I have. So this is the original B's plus all the new B's I'm going to get. So the whole thing represents the total number of B's. There you go. And that was the last one. So some good examples here. You just got to practice. This is like those sections in chapter 3. Just start practicing these. Just remember, when you're doing these, and that was illustrated in some of those examples with the algebra. Let me go back up to this. This is your list. If you run into an integral, if you end up having to add functions in here, remember, we can split the integral up into pieces like I did below. So that's fine. But other than addition and subtraction and multiplication by a constant, right? I could have like a random 3 multiplied and just take it out. You've got to make the integral that you're dealing with, the antiderivative you want to do, look exactly like one of these to use the rule. Not messing around. Not close to one of these. Not, come on, it's really close to one of these. Nope. You got to make it look exactly. What do I mean by that? Just to give you some specifics, because I know that's in general. We do not know how to do this. This is unsolvable for us right now. Now, you might think like, oh, I know trig identities to kind of try to get rid of that 3. And okay, that's fair. Something like that could work. But even just a tiny little 3 added in here means this rule does not work. Okay? So this integral is not equal to sine of 3x plus c. This is not how this works. I lost my plus c. Plus c. Here we go. So you've really, you've got to only use these rules if they are exactly in the right form. Now, if I had a 3 in here, that's okay, remember, because I can take a constant multiplied and I can move the constant out. Now it's 3 times the integral and I can use the rule. But don't mess around. These rules are only to be used in their exact form. Precision. So just be super careful with that. You run into a problem you're not sure, it just means there's an algebraic step you're missing, and just ask me when you get to that point and I'll show you what the algebra step is. It's usually something with a, rearranging terms. If it's a fraction, you just have to take the bottom and divide, maybe factoring, multiplying things out if they've already been factored and there's no fraction. Common algebraic things. So practice. You have any questions, let me know, and I'll see you in the next video.